what would happen if we took a pendulum-driven clock that keeps perfect time on the Earth and put it on the moon? Now, this is a pretty typical problem in introductory physics. Now, the way this usually goes is we're going to say if some amount of time, I don't know, maybe 12 hours goes by on the Earth, we want to know how much time the clock is going to report have gone by. Now, since this is a pendulum-driven clock, this entire problem is driven by the pendulum equation, which relates the period of a pendulum to its length as well as the acceleration due to gravity. Now, the issue here is that if we take a clock that's been designed to keep perfect time on the Earth, where the acceleration due to gravity is 9.8 meters per second squared, and we put it on the moon, where g is only 1.63 meters per second squared, the clock isn't going to run at the right speed, and therefore the dials or hands on the clock won't move correctly. Now, you'll notice in this problem, we haven't been given any dimensions of the clock. We don't know the length of the pendulum. But to make this problem a little bit easier and to clear up some misconceptions, what I want to do is take a clock, and let's imagine this clock had a pendulum with a period of exactly 1 second on the Earth. You see, applying this period equation to our clock on the Earth, if we say the clock, when on the Earth, has a period of exactly 1 second, then that means the length of the pendulum is 0.248 meters. And the reality is, if you look around, some people actually solved this problem without ever solving for the length of the pendulum. They just keep it as a variable, which is fine. But I think it leads to some misconceptions later on down the road. But imagine now we took this clock and we brought it to the moon. Since it's now on the moon, it has a different acceleration due to gravity. The period of the clock on the moon is going to be given by 2 pi times the square root of L, that is our 0.248 meters, over the acceleration due to gravity on the moon. That's 1.63 meters per second squared. Now, solving for the period of the clock on the moon, we get that period as 2.45 seconds. And this is where I see the confusion in this problem start to arise. You see, we know the period of the clock on the Earth as well as on the moon, but what do we do with those two values in order to figure out what the clock is actually going to read after a certain amount of time has elapsed on the moon? You see, really all we found here is that it's going to take 2.45 seconds on the moon for the clock to say 1 second has gone by. Now, it's not that time on the moon is actually going by more slowly than it is on the Earth, it's just that our clock is running way too slow, or 2.45 times too slow. Or to look at it differently, if a full 12 hours went by in real time, our broken moon clock would say that 12 divided by 2.45 hours had gone by. Now do the math on that, and that works out to be 4.89 hours. And realize that's a little bit useless because we don't ever deal with decimals of hours. But converting 0.89 hours into minutes would get our moon clock says that only 4 hours and 53 minutes would have gone by. And one of the cool but also confusing things about this problem is that the length of the pendulum doesn't actually matter. We could have kept this as L a variable and it would have factored out through quite a bit of algebra. But I think having a clock with a period of 1 second makes this result of 2.45 a little bit more tangible and therefore a little bit less confusing when we get to the hard part of the problem, which isn't actually dealing with a pendulum. It's really just dealing with what does this difference in times actually represent. So in short, regardless of how much time you're dealing with elapsing on Earth, if you take that total time and divide it by 2.45, you're going to get the total time that some pendulum clock reports has elapsed on the moon. So I hope you found this useful. And on that note, that's all for now.